Analyzing graphs. Before we begin to analyze graphs, it is worth our time to synthesize in a concise form what we already know. So for a function f that is twice differentiable, meaning its first and second derivatives exist, these derivatives will reveal a vast amount of information regarding the graph of f. So let us recall what the information is. Start with the first derivative. Stationary points are values of x in the domain of the function where the first derivative is 0. Extrema occurs at these stationary points. Here's an example where we have a absolute minimum, a type of stationary point, occurring at x equals 2. Singular points can also be gleaned from knowing about the first derivative. Singular points are values of x in the domain of f where the derivative is undefined. Sharp corners usually occur at stationary points. Here's an example at x equals 2 where the derivative is not defined because we see a singular point as evidenced by the sharp corner. Now, moving on to the second derivative, what does the second derivative reveal about a graph? Well, here's a function. F of x is x cubed minus 9x squared. Here is the graph of the function provided. And where the second derivative is positive, the graph is concave up. So here our second derivative is greater than 0. Where the second derivative is negative, the graph is concave down. So here is where our second derivative is negative. Inflection points are points in the domain of the function where two characteristics must hold. The first, the second derivative of f must be 0, and the graph of f must show a change of concavity. So this could be concave up left of x to concave down right of x, or the other way around, concave down left of x to concave up right of x. Notice we go from concave down to concave up, so our inflection point we may find by setting the derivative to 0 and verifying this change of concavity. Moreover, at critical points, say x equals c, the second derivative evaluated at c is positive tells you you have an extrema where the graph is concave up. So that means at c, because it is a critical point, we are taking a look at the existence of a minimum. And at critical points x equals c, where the second derivative is negative, because you are dealing with a portion of the graph that is concave down, you must be at a local max. So there is a relative max at x equals c. In this case, 0. Well, let us use this information to perform a host of tasks from nothing more than knowing information about the first and second derivative. Our function is x cubed minus 3x squared. We want to sketch the graph, but in doing so we want to analyze it. We want to recognize the x and y intercepts. We want to recognize the extrema. We would like to point out any points of inflection if there are any. We would like to see the behavior near points where the function is not defined if there are any. and we would like to discuss the behavior tending to infinity, the end behavior. So let us begin. Let us start by taking the function, setting it equal to 0. We will factor out x squared, and when we solve, we have x equals 0 and x equals 3. Here are the x-intercepts. We can find the y-intercept by substituting in 0 for x, and we get back 0. For the extremer, we take the first derivative. We get 3x squared minus 6x. We set the first derivative equal to 0 and proceed to solve. Now, unlike inflection points, as long as these solutions are in the domain of the function, we would then have the locations of the extrema. Factoring out an x, we have 3x times x minus 2 is 0. And solving, we have x is 0 and x is 2. This is the location of the extrema. To describe points of inflection, what do? We begin by taking the second derivative. Second derivative of f is 6x minus 6. Now, two characteristics must occur. First, we have to see where this second derivative is equal to 0. So we set the second derivative equal to 0, factor out a 6, and then we proceed to solve. And find x equals 1. Now, this is not a point of inflection necessarily. To have a point of inflection, I must have a change of concavity occurring at x equals 1 as well. So we evaluate our second derivative left of x equals 1 at 0, and we find the second derivative to be negative 6. We evaluate the second derivative right of 0 and find the second derivative to be positive 6. There's our change of concavity, going from concave down to concave up. Now what we want to do is take a look at behavior near points where the function is not defined, but we gloss over this because our polynomial function, its domain is negative infinity to infinity. That leads us to end behavior. What is behavior tending to infinity? Well, as we take the limit as x approaches infinity, that would be infinity. And we take the limit as x approaches negative infinity of this cubic, that's negative infinity. And by the way, we glean this very quickly by knowing that we have an odd degree polynomial and we have a positive leading coefficient. So we have a visual in our mind. As we move to the right, one branch goes up. As we move to the left, one branch goes down. Well, let's recall what we have so we can proceed to graph. What have we found out? The x-intercepts, shaded in blue, are 0 and 3, their occurrences. The extrema occur at x equals 0 and x equals 2. But moreover, we have an inflection point at x equals 1. So if you recall, when we evaluated the second derivative at 0, the result was negative. Concave down is that portion of the graph. So it looks like we have a local maximum. And if you recall, the second derivative evaluated at 2 is positive. The graph is concave up at that location. So we must have a local minimum. We also know the end behavior. As x increases beyond bound, the branch goes up. The limit as x approaches infinity of this third degree polynomial function is infinity. And as x decreases beyond bound, gets large negative y's, the limit as x approaches negative infinity of this third degree polynomial is negative infinity. The graph goes down. So synthesizing this information in terms of a graph enables us to recognize the x-intercepts, which I will highlight, at 0 and 3, the local maximum, which I will highlight at 0, and the local minimum, which I'll highlight here at x equals 2. And because left of x equals 1, I end up with a graph that is concave down, and right of x equals 1, I end up with a graph that is concave up. I must have an inflection point at x equals 1. And my end behavior, showing that I have, as I go to the right, a branch going up, and as I go to the left, a branch going down, I can quickly see the key characteristics of this third-degree polynomial. Let us look at a second example, one that is not polynomial. That is not a function that's a polynomial. F of x equals x plus 4 over x. Now we'll follow the exact same rubric. To find the intercepts, we take the initial equation, set it equal to 0, proceed to solve for x. So I'll choose to find a common denominator. I have x squared plus 4 over x. Now where the expression is equal to 0 will occur when the numerator is equal to 0. I have no x-intercepts. Next, I find the first derivative. Derivative of x is 1, and the derivative of 4 times x to the negative 1, bring the negative 1 out front, times 4x to the negative 1 minus 1, or the first derivative is 1 minus 4 over x squared. To find extrema, we set this derivative equal to 0 and proceed to solve. Using the same method we used a moment ago, we'll find the common denominator. And we have the equality x squared minus 4 over x squared equal to 0. Where this expression is equal to 0 will occur when the numerator is equal to 0. We have extrema at plus and minus 2. Now on to points of inflection. Oh, excuse me. We have a situation where a student may be tempted to think about a singular point at 0. But x equals 0 is not a value that's in the domain. So x can never be 0. Our original function does not allow us to place a 0. So we end up with extrema at plus and minus 2. No singular points. Now, moving on to points of inflection. We take a second derivative. Derivative of 1 is 0, and we're left with negative 4 times negative 2, x to the negative 2 minus 1, or minus a negative 8, x to the negative 3. In other words, our second derivative is 8 over x cubed. The points of inflection will occur when your second derivative is equal to 0. There are no points of inflection. But we need to be very careful here about how we proceed next. I don't want to take a look at just jumping to where the behavior near the points where the function is not defined yet, because I do recognize that my second derivative shows a case where when x is equal to 0, it's undefined. Now, thinking about this for a moment, x is not equal to 0. Anywhere in our domain, we have real numbers except at 0. So the likelihood of an asymptote there is pretty high, and when you have an asymptote, it is possible to have a change of concavity occurring along that dashed line. In other words, left of the asymptote, you may be concave up, right of it, you may be concave down, or vice versa. So what I'm driving at is we pause for a moment and we evaluate the second derivative, both left and right, of where our function is not defined. Now I'm going to choose strategically points left and right of 0. I'm going to choose -2 because I will kill two birds with one stone. I will not only recognize that I get back a negative value, but I've recognized that I'm concave down, and I'm also saying to myself, gosh, this location of an extreme value occurs where the graph is concave down. My visual in my mind is that of a local maximum occurring at x is -2. Killing two birds with one stone. We know about the concavity and the type of extrema. Now I want to test my second derivative right of x equals 0. So I substitute in x equals 2 into the second derivative. I find the result to be positive. And again, this tells me that I'm concave up, and therefore at x equals 2, for this extrema, I must be at a local minimum. Now I move on to say, okay, what is the behavior near points where the function is not defined? Well, it's not defined at 0. So when you take a look at the limit as x approaches 0 from the right, we end up putting in positive numbers that near 0, meaning we get infinitesimally close to 0. And we find that we have this quotient getting large beyond bound. And so the limit tends to infinity. Evaluating the left-hand limit as x approaches 0, we put in values that near 0, getting infinitesimally close, but are negative. And we find that this particular quotient gives us a result that this limit is negative infinity, gets small beyond bound. Well, what's left to do? Well, what is left to do is to look at the conclusion. We must have a vertical asymptote at x equals 0. Lastly, let's look at the end behavior. As x gets large beyond bound, the limit of x plus 4 over x will approach infinity. So, as we look at the graph globally, as we move our eyes to the right, we expect a branch to go up. The limit as x approaches negative infinity of x plus 4 over x is negative infinity. So as we look at our graph globally, as our eyes veer to the left, we expect a branch to go down. Well, let's take a moment to recall what we have just determined. We have no x-intercepts. We have extrema at x's 2 and -2. We have no points of inflection, but since x is not defined at 0, left of 0, the graph is concave down. Right of 0, the graph is concave up. Moreover, we expect to see at x equals -2 a local maximum, and at x equals +2 a local minimum. And because we know the left-hand limit as x approaches 0 is negative infinity, and the right-hand limit as x approaches 0 is positive infinity, we know that we have a vertical asymptote at 0, but specifically the behavior near 0, both left and right of 0. Lastly, we know the end behavior. As our eyes dart to the right, branch goes up. As our eyes dart to the left, the branch goes down. Putting it all together, what do we see? Clearly no x-intercepts. No points of inflection. No points on the curve where as you move from left to right, there's a change of concavity. But there is a change of concavity as you move past the vertical asymptote. You go from concave down to concave up. And at x is -2, you have indication of a local maximum, and at x equals 2, you have indication of a local minimum. Now this graph is deceiving. It's a good thing we have derivatives to help us, because without the notion of where the local maximum and minimum occur, from the appearance on the graph, it would be hard to determine exactly where the extrema were. Now, behavior at the vertical asymptote shows that when you take values of x near 0 but left of it, we have a branch that goes down. And when we take values near x equals 0 but positive, we have a branch that goes up. Lastly, the end behavior says that as you move to the right, we have a branch that goes up, and as we move to the left, we have a branch that goes down. Again, very lucky we have calculus to help us, because from this particular window, I don't think the exact locations of the extrema, nor even the end behavior, are blatantly obvious. Last function, f of x equals x minus the natural log of x. Let's begin. We know the procedure, right? But before we begin, we have to say to ourselves, well, wait a second. Our domain is only for values of x greater than 0. So we're only worried about the open interval 0 to infinity. We have to keep this in mind all the way through the process of analyzing both the first and second derivative, as well as limits. To find the x and y intercepts, what do? Well, we take our equation, set it to 0, proceed to solve. X equals a natural log of x. Now I'm going to change its form. I'm going to go from logarithmic form to exponential form. E to the x is x. And e to the x is always greater than x. We have no x-intercepts. Now we look for extrema by taking a first derivative. 1 minus 1 over x is the first derivative. Let's set our first derivative equal to 0 and proceed to solve. Well, in proceeding to solve, we get a common denominator, as we did previously. And where the first derivative is equal to 0, well, we glance at the numerator. This will occur at x equals 1. And so what did we call these types of points? This would be the location, correct? This would be the location of the extrema, max or min. So we say to ourselves, we have a stationary point at x equals 1. Do we have a singular point? Well, our first derivative is not defined at 0, but remember our domain. Since 0 is not in our domain, we have no singular points. To determine points of inflection, we begin the process by finding the second derivative, which would be negative 1 times negative 1 x to the negative 2, or 1 over x squared. Setting it equal to 0, clearly we have no inflection points. But we must stop and say we would like to know about the concavity of the function. So we choose a value that will, for us, kill two birds with one stone. I'll choose where the extrema occurs at 1, so I can not only plug 1 into the second derivative and say to myself, I know my graph is always concave up, but at x equals 1, I visualize concave up and see that I must have the existence of a local minimum, a relative minimum, if you will. Behavior of points where the function is not defined. Well, the domain is the positive numbers. But I will go to the left edge of the graph at 0 and see what happens at the boundary, if you will. Now, I can only take a right-hand limit, so I will take a limit as x approaches 0, as x nears 0 from the right, and I find it's infinity. Now, think about that for a second. As you approach 0 from the right, the branch goes up. Now, there's no vertical asymptote, there is a vertical asymptote, therefore, at x equals 0. All that's left is to find the end behavior. Well, as x approaches infinity, the limit of the function is infinity. And that's all we have to worry about, since our domain is just positive numbers. So let us recall what we found out, but begin by saying we're on the open interval 0 to infinity. We're only dealing with x greater than 0. We know we have no x-intercepts. We know at x equals 1 there's an extrema. We know we have no points of inflection. But we also know that the graph is concave up everywhere. And because it's concave up at x equals 1, which was the actual location of the extrema, there must exist a local minimum there. We know there is a vertical asymptote at 0, and we know the end behavior. As x gets large beyond bound, the y-coordinates get large beyond bound. As our eyes scan to the right, the branch goes up. Visualizing the graph, we see the graph only sketched when x is greater than 0. It is not blatantly clear from the graph that you have a minimum at 1. I mean, that minimum isn't necessarily at 1 visually. You could guess it to be in several locations, I suppose. But with the calculus that we have, we know that the local minimum occurs at x equals 1. We have a vertical asymptote at x equals 0, and the end behavior suggests that as our eye scans to the right, the branch goes up. It goes up slowly, but it does go up. Thank you.